Hello everyone, welcome to my channel. This is Aurelia NEET with me, class 11. So today we're going to see the chapter Newton Law of Motion. So as I said, this is not just a channel that will make you see a lecture. This is a channel where you can learn with the theme of lecture. So topics we are going to cover is Newton Law of Motion, impulses, linear equation, and momentum and the normal reaction. And all these we're going to cover in further up class. Now we are going to do with Newton's Law of Motion. So I want to say all my viewers, I know many viewers are seeing my video. Kindly subscribe. That makes me so motivated to take more videos. So kindly subscribe to my channel. That is Aurelia NEET with me class 11. Force. So first we'll see what is force. Force or push or pull. Cause of motion. This man is going. So cause of a motion. And a vector quantity or Newton. So Newton was first. That came before the force. So let's see some derivatives. Let's see some derivatives, guys. So some derivatives. Let's see. What is weight? That's easy question. What is weight? Maybe like mass and all. No, it is the gravitational attraction of the earth. So this is the earth and this is the mass, and it is a gravitational attraction to the earth, denoted by what? W, denoted by another second, denoted by W. That is the most ineffable thing what you can see in a earth. So that is the acceleration, that mass body G and acceleration G, that is 9.8 ms. We already know that things. So it is always direct vertically downwards. So it is done vertically downwards. Next one is normal force. So what is a normal force? So let's see what is a normal force. Normal force. That's quite different. When two surfaces are in contact, then exert force on each other. They exert force each other. Such force are known as contact force. So they are saying what is a contact force. So they are saying what is a contact force. So contact force, let's go with a simple example. So contact force is like a normal, when two surfaces are in contact, they exert a force on each other. So this is a surface, this is a surface, you can see, and this is a surface, example, you can see. These two exert the force on each other. These both exert the force on each other. The force exert on each other. This is called the, what is this called? This is so called the constant force. So contact force. So next we are going to see is the normal force is the compound of contact force that is perpendicular to the surface. So as we saw, this is a surface. So this is a surface. The normal force is a compound of the contact. So the normal force is a compound of contact that is contact that is perpendicular to the surface. That is a perpendicular. This is a perpendicularity that is perpendicular to the surface. To the surface, they act into the body or towards the body. So it act into the body or towards the body. So it is denoted by letter N or letter R. So it is denoted by letter N and letter R. So that's cool, guys. So let's see next. It is very easy. Next one is very easy, and most of us really like the next one. So anyone can guess about it. Any guesses? That's nothing. Tension. That we have, that the moment we have is tension. Oh, this girl is taking a class and all. Okay guys, don't care, I'm not kidding, but it's okay. The tension, the force exerted by the end of the torn string. So have you guys seen a torn string? Have you guys seen a torn string? I'll see, show. This is a torn string. Like a potential, we would see it in the class 9 Keep it studying. This is a torn string. Okay? This torn string. A rope or wire that is in the tension. These is connected by a tension. It's not like tension what we face. It is something a different tension. So what it is? So this is a tension. This is the tension. Means it's concentrically helically done, and this place is called that tension. The contraction. You can see the rubber band. Right? If you girls or boys, you have seen the rubber band, right? The rubber band we have tension when we pull it away. That is what we call a tension. Okay. So the direction of this force is applied. The object is object to which it is applied. The direction of this force is away. The direction of the force is away from which it is applied. It is denoted by T. It is denoted by what? It is denoted by T. So if the rope or tension is the force which is one part of string which is pulled. So I need everyone to note this in a neat point of view. Note that unless stated otherwise, string will always assume to be massless. So string will always be massless. Unless and until they are saying the string is always massless, and hence tension as a string will be same throughout the length. So the tension will be throughout the length same. Tension throughout will be same. Okay. Thus the string will pull the body connected to two ends with equal force. So here if you pull it, the both will be like in equal force. So that's a simple concept. Then we are going to see the spring force. We're like, not only we studied the tension force, again what spring force, what they meaning actually, what they may coming to say actually, it is not, it is spring force. The force exerted by spring may be represented as, the force excreted like spring force, the force exerted, sorry, it's not excreted, it's exerted, like a biology student, right? By spring may be represented as, this is so important, represented as F yes is equal to minus kx. So k is like mass and x is not force, where x is the length, x is what? X is length, and k is spring constant. X is mass, yes, as I said, mass, spring constant. So next we'll see the inertia. That's an important topic for our class. Inertia. So inertia is a word that means that it is an inability of a body to change its state or rest or of uniform motion or its direction by itself. Internal property of matter that resists the state of change. Example, if you see this truck going to hit, of course that man in the truck will put the brake. The resistance we're having, that's called inertia. Let me make it clear, very much clear. It is the property of an object to resist the change in its state of rest. So, I'm going to say in a very simple manner. This is, one second. For example, this is a person. This is a person who's. This is a bed. Okay, it's a bed. I'm going to give you a very simple example. It's a bed, and you are sleeping on it. You are, of course, sleeping on it. You have a lot of hair. Okay, you are sleeping on it. It is the property of an object. It's a your object. So you are an object that to resist the change in a state of rest. So suddenly an earthquake is coming. Let's assume it's an earthquake. Suddenly there's an earthquake. The heavy mass of earthquake is there. It's very unreal. No one has said such an example in my teachers or anything, but I'm explaining it because it's what I understand. This is a change in a state of rest or uniform rectilinear motion. So suddenly you started to get a shaking, like oh, you can start shaking. Like it's so complicated. Like what she's doing, is she mental or what? No, I'm not mental, but I want to say. So it's simple. So now we can remember. You're sleeping on a bed. You're in the rest motion. Suddenly earthquake is coming. You're changing your state of rest and you go in uniform. But it's not like you're sleeping, you're taking rest. It's any object that is just standing or reticulating. Like any object that literally stands. This is a mountain. It stands like that. So let's state it. It is a property of an object to resist the change. It resists the change in the state of rest. You're sleeping, that time an earthquake is coming, you're resisting that change. Why I need an earthquake right now? Now only I was sleeping. Or uniform rectilinear motion. So the state of rest or uniform rectilinear motion. This is not a concept. That sleeping, that resting guy is not a concept. That is easy for memorizing the statement. That's all. That's not a concept. The concept is here. A man in a bus is inertia, suddenly it falls car. That's an inertia. It's not like you standing and don't write this in the exam. I just for remember the statement I said this example. Okay. So let's see what is that definition. So anyone can you see? Can you say that? Yeah, try to say yeah. Yes. So like if you don't get it, again I'm gonna say note it so carefully. It is a property of the object to resist the change in the rest or change in the uniform rectangular motion. So it's enough. So today, inertia of an object is directly proportional to mass. That is so important, guys. The inertia of an object is directly proportional to mass. How come it can happen? Let's see. So an object is here and another object is here. The object this has more mass. This has much more mass. So this is an object. This is inertia of an object is directly. So inertia, this is inertia directly proportional to what? Mass. Proportional to mass. The inertia is directly proportional to mass. So if it's heavier object, it has a high inertia. If it is a light object, it has a very low energy reaction. So there is 3 types of inertia. So mark my words. So this for mass is a measure of inertia and translatory motion. So mass is a measure of inertia in a translatory motion. Mass is the measure of inertia in a translatory motion. Which is a measure of inertia in a translatory motion? Mass is the inertia in the translatory motion. So, the heavier the mass, large the inertia. The lighter the mass, less the inertia. The type of inertia. We want to see the type of inertia. That is inertia of rest. Inertia of rest we already saw. Inertia of motion. Inertia of direction. This is very important. So from here we can see that object at rest, state of object as a flexed state changes, inertia act. So this is a cup. You have seen this experiment, I guess. They'll take this board, so the ball falls down. So this is a great experiment, like many of them did in a childhood. Taking a cup of paper. We have seen in the class level 9, I guess. So this is an object. Here comes the gravitational force. Okay. So I'm removing this board immediately. The ball is dependent of the cardboard. The ball is not standing, like it's not flying in the air. It is dependent to the board. Isn't it? Yeah. The board is dependent to what? The glass. So as we know, the ball is dependent to the board. The dependence of that board is taken away. So that time the ball falls in. It doesn't mean we're putting pressure on ball, we're putting the ball, taking the ball or putting in water. Because of the effect of the base, it doesn't rest, it takes away. So you can also notice, if you take that board away, take at least a second of fraction of minute to get fall into the water. You have seen that, I guess. So let me get an example. So I am sleeping in a net. Okay, I'm sleeping in a net, the beach nets and all. Suddenly there's full of leaf. There is whole sum of leaf on that, on the whole sum of leaf in the net. Suddenly I'm falling to this. By a fraction of time, the net will go down. The net will go down. The leaf for a second stands in the ground, and suddenly leaf also falls down. That is called the motion in the rest. State of motion in the rest. So motion, as you always saw, object state of motion as a text or running, it will go forward. The forward jerk, for that I'll give a next example. Or how many of you are taking a school van to school? I want to see. If you're taking a school van, kindly see. This is you, okay? This is you. You're so cute. You have a lot of hair and you're always smiling. Okay, this is you. You're standing in a bus. You're holding that ring or that top thing in your bus. You're holding this. You're holding this thing. Okay, you're holding this. Suddenly your van uncle is putting. What is that? Brake. Your body, of course, your body is connected to the base of the bus, but your upper body is not connected to the base of the bus. It is connected to your leg. So leg has the power to stand, but your body will jerk. You will go an inch backside and come, not fully, you will not go an inch backside and will come friend. That is called inertia in motion. That's called inertia in motion. The leg, one part will not move, second part will move. So I'm going to give you the real statements for the all three. So kindly note in your notebook. For the inertia of rest, it is the inability of a body to change its state, rest by itself. Inability, don't forget the word inability of a body to change its state on the rest. Example, passenger starting in a stationary bus experiencing a backward jerk when the driver starts suddenly putting. This happens because of the feet of the passenger is contact with the bus and into the motion. The upper part of the body continues to remain in the inertia. This is for rest. Okay. The next one, it is the inability of a body to change its state of uniform motion by itself. The last one was inability of a body to change its state by itself. That's all. By inertia of motion, the statement is given like, it is inability of a body to change its state of uniform motion by itself. It's a uniform motion. That is state of rest is a uniform motion. For this an example, as I said, passengers standing in a moving bus experience a forward jerk. As I said, you're moving front and backward. This happens due to the contact of feet. As I said, the leg of the passenger in contact with the bus rest along with the bus, and the upper part of the body continues its motion due to the inertia of motion. If your driver uncle put brake, no, you'll go back and come front, that's all. The driver uncle stops. Again, if you take, no, you'll have another little jerk. Okay, next. We're going to see inertia of direction. This is very, very important inertia. It is the ability of a body to inability of a body. It's everything is inability. Okay, it's an inability of a body to change its direction by motion by itself. So object is in original direction. The direction changes. Inertia turns. So when a stone is tied into a string, so we're going to see that example. So I'm having a stone. So I'm having a stone here. So this is a damn stone. I'm having a stone. It's tied to one end to the string is whirled in a circle. So this is a stone, and the one end is covered. So the one end. So one end of the circle is like ball is cut like this. Then you're fully rotating the ball. In roll. And the ball, no, it will go like from here, it will go like here, and from here it will go like here. With the connection, you know how it feels like putting an ID card in the air and rolling it like something. It will go like this, isn't it? The stone flies along the tangent of the circle. So this is a tangent, so it will all fly in this direction. It all fly in this direction. Okay. This is because the pull of the string force the stone to move in a circle. But if the string breaks suddenly, your mother is coming in. You are not studying and playing. She's asking and she's cutting this thing. You know what happens? The ball will go and fly. The ball will go and what happens? The ball will fall down. While the ball fall down with the string. Just like ringa poses. No ringa poses. Then ringa poses. That game. Like that game. The ring cuts and it falls down. That's all. For like tug of war, I can take it up. So next, a person sitting in a moving train throw a coin vertically upwards. This is a very important thing in any river. So this is a seating chair. This is another seating chair. We're going to Kerala. So everyone is going to Kerala from this train. So overall going to Kerala, I'm gonna comment down. So, and this is you sitting. This is your friend, and this is your sister or brother. Okay. So you are sitting here, and suddenly you are going to play, and you're putting a moving train. You throw a coin upwards. This is a coin. You're throwing it upwards. So this is a coin up and up. It falls behind him. You're this one. This is you. If the train get accelerating, if it accelerate, then the coin falls back. Like we'll joke, no, the coin falls back of you. Okay. So next, it will. So now this is your brother. He's laughing. Your friend is laughing. Haha. You cannot do that. No, I will do. Our train is suddenly putting acceleration. So the coin came back. So now your friend is trying. He's taking the coin. He's throwing it. Suddenly it retraces. So it falls in the head of your sibling. It falls in the head of your sibling. How? The retreats that take back up. Suddenly a station came so that he put the acceleration, so it fallen back. Suddenly he's taking the train. That time your friend started to play and it was put in your sibling's head. Now it fell into the. So then again he stopped. Your brother was crying and you all stopped this game and they both went to some seat and you are again here to try how this game. So you again had a coin in your hand. So you again have a coin in your hand. You're taking it back. It fall and so if the train is moving with uniform, the train is moving with the uniform velocity, they're going to another junction. That time it correctly falls to your hand. You'll be shocked. Well, hell, bro. My brother and my friend was there. It didn't fall. Why does it fall now? So again, after a few times, his train slowly come to the rest. Then he tried again. It came back. He was shocked. He was what? He was shocked. How could the hell it happen? Then that's the story, guys. That's enough. So that was the story. What happened to that guy? So that was so fun. So now we can remember the whole train scene and all. So now we see the Newton's first law, or law of inertia. Let's enter to the first main thing. So here, object at rest will be at rest, or in a motion will be in motion until and unless an external force act on it. So this is a very good example. You are a freaking NEET aspirant, aren't you? So you are a freaking NEET aspirant. So you are a NEET aspirant, and this is your freaking mom or dad, anyone. They came to your room and they saw you sleeping at like 9:30. They were really shocked. Why this boy is sleeping 9:30? He's a NEET aspirant. He needs to study and putting water on your face. In this statement, you can see that the objective is that you are at rest until or unless something is disturbing you, that external force your water. Okay, so let me give the exact statement for this. Everybody continue to be in its state of rest. Of course, if you sleep, you're always in the rest. Okay, it's not like that. You will see. A uniform motion in a straight line, or in uniform motion straight line, your train is moving in a straight line, unless and until like a net external force change in it. That change is called Newton's law, first law of motion. Importance of first law. What is importance of first law? Let's see what is the importance of the first law. So, importance of first law. It gives the concept of inertia and force and enables us to decide. It gives the concept of inertia and force and help to decide. From this slide can be concluded that the acceleration of an object is zero if there is no external force. If it is having no external force, then no acceleration. No external force means no acceleration. These two concepts are very from the importance of law. So, what are the two importance of the first law of motion? If there is no first law of motion, we don't know what is inertia, what is force, and all. So, with the help of first law of motion, we learn what is inertia, what is force, and we also came to knowledge that there is no external force, means there will be no inertia or acceleration. So that we came to know about with the help of the first law of motion. The definition of force. So let's come to we are already seen, but let's see the correct definition of force. So because of this only we got the inertia and force, right? So let's see the definition of force. Force is the physical quantity that changes or tries to change the state or the uniform motion. That's all, the simple word. The force is the physical quantity. Force is a physical quantity that changes or try to change the state of rate of the uniform motion. It defines the inertia, force and mechanical equivalent. So inertia, force and mechanical equilibrium. If the net external force of an object is zero, the acceleration will be zero. So everyone knows what it is. So we learned already. So let's see the next one, that is momentum, or also called as linear momentum. So momentum or the linear momentum is the motion of body containing in the body. So let's see. Linear momentum is the product of the mass of a body and velocity. So I'll give you a deep explanation for that. It is the amount of motion contained in the body. So momentum is amount of motion contained in the body. Quality of the motion is directly inversely proportional to what? Mass of the body. So that is E is equal to mv. This is momentum, this is mass, this is a velocity. So next one we want to see like P bar is equal to mv bar. That is very important, kindly note. And we will frequently use this formula. We will use frequently, like 98% of the chapter comes by this formula. That is so important to note. So the net force, we want to see the second law now. So I'm giving you the correct definition right now. Linear momentum is the product of the mass of a body and the velocity, that is P bar is equal to mv bar. The linear momentum is a vector. So linear momentum is a vector. Momentum is a vector quantity. It has the same direction as the direction of the velocity of the body. The SI unit is kg meter per second, CGS unit is grams centimeter, and if the body of a mass m changes its velocity from u bar to v bar, then the change in the momentum of the velocity changes like uv bar minus mu bar, that is momentum or changes in the both in the same direction. So this is like if a body of mass m changes its velocity, if a body of mass m changes velocity to u bar to v bar, the change in the momentum of body, that is delta p bar is equal to uv bar minus mu bar. Momentum of change in momentum both have same direction. For example, a stone is rotated in a uniform speed horizontal, means a thing, the magnitude of the momentum is fixed along its direction. The magnitude of the momentum is fixed along the direction. So let's see the very important thing next is Newton's second law of motion. That is Newton's second law of motion. The time rate change is the momentum is directly proportional to the effect. We already saw that by directly proportionalities. So let's see the Newton's second law of motion. The Newton's second law of motion states that the rate of change of linear momentum of body with time is proportional to the net external acting on it. The rate of change of linear momentum. The rate of change of linear momentum is directly proportional to the external force acting on it. So let's see the derivation of this formula, because many of them don't know the derivation of this formula. So let's see. The derivation be like, net force acting on the object is directly proportional to the change of linear momentum. So F bar is directly proportional to dB bar and dt, the linear momentum. So F bar is equal to K dP bar by dt bar. So you know what is K. So F bar is equal to dP bar by dt bar. So the like more momentum, there will be more force. Less momentum, there will be less force. That's the concept. So the force is directly proportional to the linear momentum, that is dP by dt. That is F bar is equal to K. K means mass. I guess mass. K we already saw. What is meant by K? The K is the spring constant or physical constant. It's constant. K is like a constant. And dP bar by dt time, that is the time. That force is equal to dP bar by dt. So more momentum, there will be a more force. Less momentum, there will be less force. This is a very basic concept of the momentum. So we are going to say the force average force. So the average force will be like, one second. So let's see the average force. So the force average is equal to delta P bar by delta T. This is very, very important, guys. The average force is equal to delta P bar by delta T. The speed of the momentum. So next we are going to see the speed of the momentum. So next we are going to speed of momentum. That is F is equal to mass by dV by dt. F is equal to mass, that is F is equal to F is equal to m dV by dt, the speed of momentum. The speed of momentum. The speed of momentum is equal to F is equal to m delta V by delta T. Another thing is that the delta P is equal to mv. Delta P is equal to mv. That P is nothing but momentum. That is K dP by T bar by dt is all momentum by time. Momentum by force is equal directly to the momentum by time. That's the speed of momentum and all motions for the definition of d and time. So here I have very small quote. It be like, you're falling from the height. Okay, so it's like Vf is equal to Vi plus At. This is a comedy one. You're not dying because Vf is equal to Vi plus At.
Who phoned exam? Huh? Who phoned exam? Henry. Share a ball.
The final velocity is equal to initial velocity plus acceleration. That is not why you are getting fallen down. The momentum that gained in the way of the fall is equal to delta P is equal to mv. The way this G is equal to delta P by mv. We are like falling down. That's the velocity of the whole G. The down will be the collision. So in this particular state, we are getting the collision. That is F is equal to mv by dt small. So that's small. So F is equal to mv by dt, that is small. So let's see the real derivation. So you all saw the basics and derivation. So let's see the real derivation from the formula of F is equal to ma. We already know what is F is equal to ma, so let's see derivation. So the F average is equal to delta P bar by delta T, that is delta momentum by delta T. Speed of the momentum is equal to F is equal to m delta V by delta T. The P bar is equal to m and V. So the falling down is due to the collision, and that is delta P is equal to m and V. Down there be a collision, that is F is equal to mv by dt. Second law of derivation. So we are going to see the derivation. So that is F bar is equal to dp bar by dt bar, that is the momentum by time, that is momentum by time. So that is momentum by time. So the F bar is equal to d by dt mv bar. We already know this. And the P bar is equal to, we already saw that P bar is equal to mv bar. So we're putting it here. After putting it here, like d by dt in the place of the P, we are putting the mv bar. So the F bar is equal to dmv bar by dt plus mdv bar by dt. And I want to mention that mass is unless or until said it is 0. So these velocity by time, that is acceleration, is 0 unless it is mentioned. So we're gonna cancel it. So we are getting F is equal to m dv by t bar is equal to dt. So what is dv by dt? As I said, what is dv by dt? That is acceleration. So F is equal to ma was created in such a way. How is SFM as ma was created in such a way? For CBSE students, it's very, very, very important. If you're a repeater or any other coaching, so you don't need that. With NEET exam, they're not going to ask, but for the CBSE point of view, it's very, very important. So let's see a problem related to this. So kindly note the question. A hole pipe has a cross-section area of 10 centimeter square and water of density 100 kg meter cube is flowing out of it in the speed of 10 ms. Find the force required to hold the pipe steadily. So this is a question, so I guess everyone has noted the question. If you want, you can go back and hear it again, or else I'll say. A whole pipe has a cross-section area of 10 centimeter square and a water of density 100 kg meter cube is flowing out of pipe the 10 ms. Find the force required to hold the pipe. That is, this is a pipe. The pipe is extended. The water, that is just flowing from here, it falls down. So that is a coefficient. The F is equal to dp by dt, that is momentum by time. So the volume of the volume of the water that comes out by the time is equal to AVDT. That is area of cross section and VDT, we know. Then mass is equal to area of cross section by AVDT. So the area of cross section by AVDT V. So F is equal to dp by dt, that we already know its momentum, is equal to area of cross section of AB square. So finally I need the answers in the comments. So the first question for I need answers is comment, and the final answer I will say. If you get the steps, it's okay. If not, you're not getting the steps, or I didn't understand, I will make a special shorts for the video that the answer is for like 100 Newton. And if you didn't get that, kindly say. I will explain very clearly in the step by step in the next shorts. I want, if you want, I will put it. Next, okay, let's see some other sum, and let's see what is importance of second law of gravitation. This law gives us the measure of force and the unit of force and divide from the law. This is a real law of motion because both first and third law can be derived from this law. Both first and third law can be derived from this law. So let's see another question that is a very, very important question for the class 11 NEET. A force produced, so kindly note it. A force produces an acceleration of 16 meter per second in a mass of 0.5 kg and an acceleration of 4 ms square in an unknown mass when applied separately. If both the masses are tied together, what will be the acceleration under same force? I'm repeating. A force produces an acceleration of 16. So A is equal to 16 ms, 5 ms 1 meter per second. A mass m is equal to 0.5 kg and an acceleration of 5 ms in unknown mass. This is a separate one. A is equal to 4 in the unknown mass. Unknown mass. If both the masses are tied together, what will the force? As I said, the contact force both together and all. That F is equal to ma. That is 0.5 into 16 is equal to 8 Newton. When the both masses are joined, the same forces act like F by m plus m bar is equal to 8 by 0.5 plus 8 by 4. That is equal to 3.2 ms minus square. So I know the handwriting is worst. If you want, I will take again next class because session is running the time out. So I'm not taking it right down. I'll still take you to that. So this is the very short thing what we saw in the long derivation form. If you want, you can take this notes also. So thank you for watching my video. Thank you so much. If you want more sums, kindly I'm dropping out my Instagram ID as well as the Instagram ID as well as my email account. So if you want any, you can text me. So that is achuvmoney.smi. That's my Insta ID. And if you want to me getting something email, if you want to get to some PDF of biology or anything, you can contact to my email. That is Akshaya prpccnt@gmail.com. So I'm the only official for this account. So you can contact me at any time by this account, and that's my Instagram ID. So I hope everyone to subscribe, like, and share to your friends if you like it, and follow me in Insta. Follow me in the Insta part. Follow me in the Insta page, and as well as following the Insta page, as well as you can text me at any time for the email. So I will be replying to email immediately. If you have any doubt in any sums, I will be taking a special video and I will be sending in the email itself. It's very completely free without a for only class 11 and only the chapters which I teach, which I have teached, is only will be only clear doubts. The doubt will be cleared only under the chapter which I teached, as well as related things. Not for class 12 or not, because I am not a class 12 student. So if you get me the questions, I will surely solve and give step-wise solution for them. Okay guys, so thank you so much. Subscribe to the channel.